definition for sequence and range of the sequence, what is the difference between set and a sequence, and some other definition for the convergence of the sequence. So let's get started. The definition for sequence: we define a function f from n to r, where n is a set of natural numbers and r is a set of real numbers. We define this function by f of n equal to xn for all n belonging to natural numbers. Then x1, x2, x3, x4, so on. This is called a sequence. Next, for example, we consider a function n to r. By f of n equal to 1 by n, it is given that the function is to be defined as 1 by n for all n belonging to natural numbers. Then what will we get? We will get 1 over n as, put n equal to 1, we get 1. Put n equal to 2, we get 1 by 2. Then 3, we get 1 by 3. Then 1 by 4, so on. So this is a sequence, right? Next, there is another example. We define a function from n to r by f of n equal to minus 1 to the power n for all n belonging to natural numbers. Now here, if you put n equal to 1, you get negative minus 1. And if n equal to 2, the power will be even, so you get 1. Again, if you put n equal to 3, the power is odd. And for odd power, this minus 1 to the power odd power, this will be minus 1. And then if you put n equal to 4, you will get to 1. So you get minus 1, 1, minus 1, 1, so on. So these are your elements for the sequence. Remember that sequence may have same elements, right? Next, now what is the difference between a set and a sequence? We have all done set in class 9th. So let's see. In a set, all the elements are distinct. Yes, if you consider a set, suppose A is your set of natural numbers from 1 to 4. So here, all the elements should be distinct. Whereas in a sequence, the elements need not be distinct, right? The elements can be repeated like we have done in this example. The elements are repeated. But if you make the set for minus 1 and 1, then your set will contain only minus 1 and 1. Only these two elements, the distinct one. This is your set. Then the second difference is that a set has no ordering. You can have set to be as 1, 4, then 6, then 2, then 5 and 3. There can be no ordering. But in a sequence, we need an order. We need a definite rule, right? So if you take your sequence, then that sequence should be as of natural number as 1, 2, 3, 4, 5, 6. So this is your sequence and this is your set. Order doesn't matter in set, but in sequence we need a definite order. Next, what is the range of a sequence? Let xn be a sequence, then range of xn consists of distinct points x1, x2, x3. Suppose here you are having a sequence, your x1 is 1, x2 is 2, x3 is 3, x4 is 4, x5 is 5, x6 is 6. So what is the range for this sequence? 1, 2, 3, 4, 5, 6. And what is the range for this sequence? The range for this sequence is? Yes, only the distinct elements, that is minus 1 and 1. This is the range of this sequence. Then there is a remark. It's a very important one. A sequence is said to be bounded if its range is bounded. Now to check the sequence whether it is bounded or not, you just check the range first, right? Now what is a bounded sequence? The first definition is a sequence xn is said to be bounded if there exist real numbers L and U such that L is less than equal to xn less than equal to u. That means if you're having this element in your sequence, then L is your lower bound and u is your upper bound. So this is your lowest, smallest element, and this is the upper one, that is the maximum element. This is your minimum, this is your maximum. So whenever this thing happens, your sequence is said to be a bounded one. Again, if you look at the example, that sequence -1 and 1. -1, 1, -1, 1, -1. What is the minimum element of this? -1. What is the maximum element of this? 1. So is this sequence a bounded or not? Yes, this is a bounded sequence. Okay. Second one is a sequence xn is said to be bounded if there exists a positive real number k such that the modulus of your elements of the sequence xn that should be less than equal to k for all n belonging to the natural numbers. So these are the two definitions for the bounded sequence. The third definition is on the metric space. Suppose you're having X to be as your metric space. Let's check out the figure. This is your metric space X. And let Pn be a sequence in X. So this is your sequence in X. It is P1, P2, P3, P4, so on. Then the sequence Pn is said to be bounded if there exists P belonging to X. So there is another number P which is belonging to this X metric space. And also you need a number K. A number P and one more number K. You need these two such that the distance between every element of the sequence P1, P2, P3, P4, their distances from this P, this distance should be less than equal to K for all n belonging to n. So this distance between P1 and P is also less than equal to K. Distance between P2 from P should also be less than equal to K. The distance between P3 and P should also be less than equal to K. So for all the elements, if this thing happens, their distances from P, if less than equal to K, we say that the sequence is bounded in the metric space. Now is the monotonic sequence. The definition: a sequence xn is said to be monotonically increasing if xn plus 1 greater than equal to xn. That means the succeeding element or the succeeding element xn plus 1 should be greater than equal to its preceding one, that is xn, right? We say that this sequence is monotonically increasing. For example, your sequence 1, 2, 3, 4. Here, if you take xn plus 1, you guess 2. So this is greater than equal to this preceding element. Again, this 3 is greater than equal to this preceding element. Greater than or it is equal to, right? And when the sequence is said to be monotonically decreasing, if you take as this 4, 3, 2, 1. Here, xn plus 1 should be less than equal to its preceding element, xn, right? Next, there is a very important concept for the convergence of the sequence. Let's look over it. We are having, you know that the value for root 2 is 1.4142 approximately, right? Just see this remark. We have considering the sequence as x1 to be 1, x2 to be 1.4, x3 to be 1.41, x4 to be 1.414, then x5 to be 1.4142, right? So on. If I guess my epsilon to be 1 by 10, what is the value for 1 by 10 in points? In decimal, this will 0.1. Then the difference between the element xn minus root 2 should be less than this 0.1 for n greater than equal to 2. Yes. What should be the value? Let's check. If I take n to be equal to 1, right, and check the difference. For n equal to 1, I'm having xn, that is xn to be equal to x1. And what is the difference? 1 minus root 2, modulus of. Write the value for root 2, 1.4142. what this difference comes out to be? This difference comes out to be, this is 0.414. Is this value less than this epsilon? Is this value is less than 0.1? No, it's not less than 0.1. So I skip this one. I take my n to be greater than equal to 2. Now let me check. Now for n greater than equal to 2, that means if I take n2, what is xn? It will be x2. So this is 1.4 minus 1.414. Let's check out the difference. What is the difference then? It is 0.014. Now is this value is less than, strictly less than 0.1? Yes, yes. What is 0.1? This is your epsilon. So this modulus is less than epsilon for n greater than equal to. From where we start our n? We start our n from 2. So I write here 2. Right? Right? Okay. In the next go, if I take epsilon to be 1 by 100, this is 0.01. Then this mod of xn minus root 2 less than epsilon for n greater than equal to. Just check. This should be 3 then. Then again, if I take epsilon to be 1 by 1000, this is 0.01001. Then this mod should be strictly less than epsilon for n greater than equal to 4. Now what is happening over there? We are observing that for every given epsilon, there exists a positive natural number n which depends upon this epsilon. This number depends upon this epsilon. So for every epsilon positive, there exists a positive natural number which depends upon epsilon such that the modulus of xn minus root 2 should be strictly less than epsilon for n greater than equal to capital N. This is your capital N. Right? So we observe that for every given epsilon positive, there exists a positive integer n, that integer n, which depends upon epsilon, such that xn minus root 2 should be strictly less than epsilon for n greater than equal to n. That means this sequence xn is converging to root 2, right? It is tending to root 2 as we take our n to tending to infinity, right? So we say that the sequence xn converges to root 2, right? Epsilon is just your small positive number which is greater than 0, right? You take your epsilon to be, you choose any epsilon, and on depending on that epsilon, that is your integer n, you say that your sequence converging to the point, whatever point it may be. For example, here this xn converges to root 2, right? For n greater than equal to n. Now what is the limit of a sequence? Just now we have defined the convergence of sequence on the metric space. Let's again revise that. A sequence Pn in a metric space X is said to converge to point P belonging to X if for given epsilon positive, there exists a positive integer n depending on epsilon such that the distance between Pn and P should be strictly less than epsilon for n greater than equal to n. Now what is this P? This P is your limit of a sequence. In this case, this root 2 is the limit of the sequence, right? Where the sequence converges, at the point where the sequence converges, that point is your limit of the sequence. Now, if a sequence converges to P, then P is called the limit of the sequence. So what we are saying that if we take limit n tends to infinity on Pn, then this will be equal to P. Or Pn converging to P as n tends to infinity, or simply Pn tending to P. Now this is very, very important remark. On what our convergence depends upon? Is our convergence depends upon only the sequence Pn? No, one more point is there. Our definition of convergent sequence depends not only on the sequence Pn but also on the metric space X. Why? Suppose you are having a sequence 1 by n. Now this sequence converges to, as n tends to infinity, this sequence converges to 0. In what metric space? In R, set of real numbers. But it fails to converge in if I say R positive. It fails to converge in R positive. Why? As 0 does not belongs to positive set of positive real numbers. 0 does not belongs to that. So this sequence converges in R only. One more sequence, 1, 1.4, 1.41, 1.414, so on. This sequence converges to, just now we have done, it is converging to root 2 in R. But fails to converge in Q. What is Q? It is a set of rational numbers. As root 2 does not belong to the set of rational numbers. So metric space is important. What metric space you are taking, that is also important. So our convergent sequence depends upon sequence itself and also on the metric space you are taking, right? Next time we will do the theorems based on the convergence of the sequence. Just get ready for that. Thank you for watching this video. Have a good day.